Physics and Astronomy at Dartmouth College in December of 2011, and he's currently an associate professor there. Ryan's main research interests include active galactic nuclei, galaxy evolution, large-scale structure of the universe, the cosmic X-ray background, and X-ray binary pulsars. At Dartmouth, he has built a strong, diverse, and energetic group of young scientists working with him on these various topics. His group reliably contributes a significant fraction of the attendees at our annual NERCON meetings, otherwise known as New England Regional Quasar and AGN meetings. And Dartmouth joined our cycle of host institutions, hosting our 25th meeting in 2015. And Ryan's collaboration with Durham University has continued, most visibly, at least to those of us outside, via the lively and interactive AGM-based conferences which ping-pong across the Atlantic every 2 years, and which I'm sure a number of you have attended. As part of our celebrations of Chandra's 20th year in 2019, we at the CXC have organized a series of talks by young scientists who have been long-term members of our community at key conferences, including the AAS and HED, for example. The aim of the talk is to highlight and celebrate Chandra's impactful scientific contributions across the full range of astrophysics. Ryan's association with Chandra and X-ray astronomy is sufficiently strong that not only did we at the CXC target him for nomination to give an AAS plenary talk for Chandra's 20th, but the AAS independently made the same decision. So needless to say, our nomination was accepted. In Seattle, Ryan gave an excellent talk to a packed auditorium covering a broad swath of Chandra science and its impactful results across astrophysics, accompanied by beautiful X-ray and multi-wavelength images. His offer to repeat his talk at CFA, Chandra's home base, is even more important than anticipated, since many of our community were unable, through no fault of their own, to travel to Seattle. So welcome back, Ryan.
Thank you very much. Hi, everyone. Thanks very much for having me here. This is lovely. And so, as Belinda said, I'm going to do kind of a reprise of the talk that I gave as a plenary talk at the AAS. Before I begin, that comes with 3 caveats. The first is I see people in the room who are there, and so you're not going to see anything new. This is exactly the same talk with a couple minor tweaks. The second one is I am almost certain it will not be as polished as it was in Seattle, because I have not stayed up in the evening practicing it 4 or 5 times in a row before I've given it here, but hopefully we can do the job. And the last thing is that this is really aimed at the sort of AAS plenary talk level, and so please excuse me if this is sort of not getting into some of the nitty-gritty details that the experts in the room here would like to hear, but that would be an entirely separate talk. Actually, that would be multiple entirely separate conferences when you really start getting into the details. And it is, I should say, Belinda let us know at the AAS that actually is the subject of the 20 years of Chandra meeting in December. So anyway, this is a very broad overview. So to begin, I'm really excited just to celebrate the 20 years of science with Chandra, but maybe the first step is just to introduce what Chandra is. It is one of the 4 original NASA Great Observatories that were launched in the 1990s and 2000s, going from the gamma rays with the Compton Gamma Ray Observatory all the way out to the infrared with Spitzer. And so Chandra is the X-ray telescope, the sort of one of those 4 great observatories that covers the X-ray part of the spectrum, and as such has been a critical component of our multi-wavelength view of the universe. When I was at AAS, the next step we found, at least to me, was I'm going to be extemporize here as we go along, was very important when trying to give a talk to the whole community, which is to ask the question, why X-rays? Why is it that you would build an X-ray telescope? I think the people in this room already know why you'd build an X-ray telescope. Most of us work on them. But it's important, I think, as we're looking forward to future missions, to motivate that to the broader community. And so there are obviously many, many different kinds of science you can do with X-rays, but I'm going to focus on just 2. The first is that X-rays probe extreme phenomena. Black holes, neutron stars, very strong magnetic fields, very high temperatures, relativistic jets, all that kind of stuff. And through the probing of those extreme phenomena can also give us a handle on fundamental physics in a way that, at least in certain applications, that we can't do in other wave bands. And then the second has to do with understanding the whole overall evolution and structure of the universe. In particular, understanding what the normal matter in the universe is doing. So this is a slide from a simulation, a visualization of the illustrious TNG simulation, showing a volume of the universe and showing the stars. This is the density of stars, which is pretty much what you would see in an optical image. But those, of course, only represent a small fraction of the total normal matter, the baryons in the universe. And if you instead show all the matter, you get something that looks like this. Instead, much more complicated. This is much more active, potentially, as it were. So this is the gas, and one important thing you can see is that the gas, and especially in the massive systems, the gas that's interacting with the galaxies tends to have temperatures of up around 1 million or 10 million degrees, which is precisely what we observe in X-rays. So I think it's not too much a stretch to say that X-rays probe the diffuse gas that comprises the bulk of the normal matter in the universe. And if you want to understand how structures form, particularly how galaxies form, the X-rays are a critical component of that, or they probe a critical component of that. Okay, so that's why we build an X-ray telescope, and some of the advantages of X-rays were known from the very beginning in the early days of X-ray astronomy, and in particular were known to the great Riccardo Gicconi, who was the pioneer of this field, and as I'm sure everyone here knows, he passed away about a month and a half ago. He won the Nobel Prize in Physics in 2002 for his contributions to X-ray astronomy. And he sort of began first through rocket flights and then the development of satellites. He began the legacy that we have with X-ray astronomy now. And one of the important things, sort of looking back at that particular legacy and looking back at the origins of Chandra, was that Riccardo was fairly prescient in terms of what it would take to actually build a really powerful X-ray observatory. So this is an image or a diagram from his 1963 proposal to NASA that laid out a program for X-ray astronomy over the course of the 1960s and 70s. And this is a 10-meter long soft X-ray telescope that would be in orbit with some grazing incidence mirrors up here, and then the detector electronics down here. It wasn't launched on a space shuttle, it was launched in a rocket, but it actually looks remarkably like Chandra. And of course, this vision got sort of further fleshed out, and then in 1976, he and Harvey put together the proposal to NASA that would eventually become Chandra. This is the cover page of that proposal. Thank you to Pat Slane for providing this lovely period photo of our Felix Chandra leader here. So, as I like to point out in the plenary talk, it's fun to show actually how Chandra was launched. This was the Space Shuttle Columbia, and showing there commanding the mission was Eileen Collins, who was the first female commander of a space shuttle mission. And so this is Chandra being released from the payload bay of the space shuttle, and you can see here, this is the telescopes up here, and then this is the inertial upper stage, which eventually fired and sent Chandra into its highly elliptical orbit. One thing I also mentioned is that this talk is about Chandra, but in the same year, ESA launched the XMM Newton satellite, which was complementary to Chandra in terms of its abilities, and really together they ushered in a revolution in X-ray astronomy. And there's many of the things that I'll talk about there have also been important contributions from XMM. So here's Chandra's orbit. It's on this very elliptical orbit, going about a significant fraction of the way to the moon, outside the radiation belts of the Earth. And when it was launched, it was named, it went from being the AXAF, the Advanced Astrophysics, Advanced X-ray Astrophysics Facility, to Chandra, named after the great Subramanian Chandrasekhar. And now we have this telescope, And as I'll show you, this telescope really revolutionized our understanding of the high-energy universe. But it's important to think about, you know, when we're the kind of people who write proposals, we actually want to understand the capabilities of telescopes. What is it about Chandra? What were its key capabilities that made it so revolutionary? And a lot of it focuses on the mirrors. This is a nice schematic of the Grating incidence mirrors showing how they focus X-rays down onto your suite of detectors. And it really is the mirrors and the detectors together that give you all this remarkable capability. So there are really three things to focus on. Primarily is the high sensitivity. Chandra has a large effective area, at least a relatively large effective area when mated with the other capabilities here. It has excellent spectral resolution over a broad energy range, going all the way from the soft X-rays, which probe mostly thermal processes, or they can probe thermal processes and diffuse gas, out to the hard X-rays, which often probe more non-thermal emission from things like neutron stars and black holes. And the key, though, really, as everyone here is aware, is Chandra's exquisite angular resolution. Half an arc second on axis. And I think the really important point, and it's something that, you know, many people, it's a point that gets made all the time, but is that Chandra's resolution is comparable to or better than ground-based optical facilities. So in the past, we had X-ray observatories, but they took these sort of big, fat images that could not be immediately and intuitively compared to the optical images that we got from the ground. And given how well developed optical astronomy is, you know, there was less utility. Now we had an X-ray telescope that could actually take comparable resolution images, and the impact of that, as you'll see, is really astounding. And so all these capabilities led to really amazing growth in Chandra science. So I've plotted here the year, and this is the cumulative number of refereed articles that comes from the wonderful Chandra bibliography database. And so the growth started out, you know, Chandra has been basically very consistently productive over its lifetime, and now there are many, many papers, 7,000 papers, 7,600, I think, and counting papers that have been produced by Chandra. So, yes, so just in terms of what I did at the AAS was then introduce this in terms of my own trajectory, although I did not here include the photos of myself, but I figured this is a friendly audience. People, you just like my family here at the CFA, so I'll add a little something. So I came into work with Chandra in around 2004 during my first work I did with Chandra data was in my second year in grad school, but then I got going in earnest on my third and fourth years. And so I found an old picture of me. Here I am looking very dapper at that time. And the amazing thing for me is that really my involvement with Chandra has spanned my entire, pretty much, scientific career. I look a little bit different now. But, you know, this is where we're at. And so it's really been the bulk of Chandra that I've had the pleasure of being involved in to see all the science happening. I also noticed that this year I actually decided not to cut my hair for a while. So my hair's almost back to where it was, which is kind of amazing. What's that? All right. No. All I'm saying is I was alive and sentient during the time that those papers were produced. But sort of another way of thinking about this, at least for me, what's kind of fun, is that you know, I guess relative to my own age, I didn't age that much. But at the time that I came in, Chandra was like preschool age. You know, like my daughter is about the same, about 4 years old. But now Chandra's in college, and you know, sort of there's been this great development of science since then, and it's been a real pleasure for me to be able to be, you know, involved in the field for most of Chandra's lifetime. Okay, in terms of some numbers, let's throw some numbers down there. So there's, like I said, over 7,000, almost 8,000 refereed Chandra papers, steadily producing well over 400 of them per year. These produce over 300,000 citations. There are 4,300 unique PIs and co-Is that have used Chandra, which this is a remarkable number. This is a significant fraction of the overall astronomical community. And we have 170 new people every year being involved in successful Chandra programs. So it's continuing to build in a whole user base of people into X-ray astronomy. So I think those numbers alone give you a sense of what Chandra's impact was. Okay, so those 7,000 papers cover a very wide range of science, and I have absolutely no hope of even beginning to scratch the surface of all the work that Chandra has done. So instead, I'm going to just emphasize a few representative results that show what Chandra can do with its capabilities, and I'll separate that on three main areas, kind of divided by astrophysical scale. So we'll start with the lives and deaths of stars, then we'll go into the growth and evolution of galaxies and black holes, and finally, large-scale structures and their cosmic history. So let's start with this first one, the lives and deaths of stars. And we'll start with a familiar place in the sky. This is Orion. So as you're all familiar, the Orion Nebula, the nearest star-forming region, nearest massive star-forming region is down there. If we zoom in on it in the optical, it looks like this. And at the very center, you can see the Trapezium Cluster. And if we zoom in on that, this is what it looks like. You have these massive young stars that have been formed inside this cloud of star-forming material. Now, it turns out that X-rays is a really useful observational tool for understanding star formation for a couple of reasons. One is that, the biggest one is that pretty much all newly formed or forming stars are highly magnetic, so they produce a lot of X-rays. And often it can be difficult to tell if you look at an optical or an infrared image of a cloud like this. It can be difficult to tell what clumps are actually things that are forming stars or newly formed stars, and what things are just sort of still clumps of gas. So the X-rays are a great way of teasing that out. They also let us do other things like probe the evolution of magnetic activity, see how that's connected, for example, to stellar rotation, many other properties. But even just identifying those young stars is critically important. So you want to take an X-ray image. Before Chandra launched, the best X-ray image of this was with ROSAT, HRI. And this is what the ROSAT HRI image looks like. So you can see right away, great, we have some stars. You can identify some of these are obviously some of the objects in the background. But we're confused in the center here. You can't necessarily separate these objects out from each other. So we come along with Chandra with significantly better angular resolution, and you get this. So immediately, I love this image because you can immediately see how much more you learn. And so this is showing now the bright stars in the trapezium, plus many, many, many young stars all around this system. And one thing I pointed out, I'm sure everybody here is familiar, but one thing I pointed out at the AAS is just that the colors, the false colors, represent the different energies of the X-rays. And so this is just one of the best studied of many star-forming regions that have been observed with Chandra. And at least, I've been on attack panel discussions, or haven't. So okay, I have heard about. No, I haven't. I'm not supposed to have heard about them either. Okay, I'll just yeah. Anyway, this is not my field, but I have heard it said that that really the X-rays is absolutely critical for being able to identify young stars, and that Chandra's capability in doing this has been revolutionary, and I think that's an important part of its legacy. Okay, so that teaches us about how stars are born and how they live. How about what happened when stars die? That's some of the most exciting things that happen to stars, especially massive stars, when they reach the end of their life. And so Chandra has made important contributions to that. Here's a famous supernova remnant, Cassiopeia A, and this is what you can see in the visible. So we have this star that exploded about 300 years ago, and it is sending a shock wave into the interstellar medium, and it's exciting this gas, which is then lighting up in emission lines, which we can see in visible light images here. And this was obviously an interesting target, and it really was the official, so interesting for Chandra, it was the official first light image for Chandra. And so this is what that Chandra image looks like. And you can immediately see lots of wonderful structure here, corresponding both to the kinematics of the shock wave, but then also emission by highly excited elements that have been blown outwards by the explosion. And so we get some information from this, but we'd like to learn more, and in particular, that question of how the elements that are produced in the star and get blown outwards, how do they get dispersed into the interstellar medium, and how actually ultimately are they created in the star themselves. That's one thing that supernova remnants can really tell you. So this is a kind of cartoon picture for what the inner structure of a massive star looks like. And when the star explodes, these different elements will get dispersed in the supernova remnant, and we would like to be able to see that structure to understand how the star exploded and how those elements were formed in the star before it exploded. So how do we do that? Well, we do it in Technicolor. This is where Chandra's spectral capabilities come in. So this is a single band image, but if we break this up into multiple bands, using more data over many years of Chandra's lifetime now, you get something that looks like this. You can actually separate the emission from many different elements. So another way of showing that, if you look at the spectrum, here's the brightness as a function of energy. And so this is showing the emission from different elements. These are all elements that are ultimately produced in the cores of massive stars. You can see these emission lines if you just separate out the emission from those individual lines, and you can see where those elements are in the explosion. And so this is a lovely graphic that was produced by the EPO office, the Chandra EPO office, which, by the way, I should just give special thanks to. Again, it was super easy putting this talk together because all I had to do was go on the Chandra Press website and just drag all their awesome images. So when they say the AAS, make sure that your talk has compelling visuals. That was not hard at all for this one. Anyway, so they have this. You can see from this these different images here where the different elements have been dispersed into the supernova remnant. And this tells us something, again, about the explosion and also about the interior structure of the star. And one of the most interesting things, and this was discovered very early on, even in that very first image or observation, is that the iron is actually somewhat concentrated towards the outside of this explosion, which is a bit surprising given that the sort of simple onion skin model would say that the iron should be produced in the densest, hottest regions in the center. And so this has been an important input into models of both fusion in stars and how a supernova proceeds. Right, so Cas A is just a wonderful object. Another fascinating part of Cas A is, of course, this bright object in the center here. And as everybody here knows, this is a neutron star. This is the compact central object that was left over during the explosion. And you really, in order to be able to detect this thing, you really need to have the angular resolution of Chandra. And now this object is confirmed to be a neutron star, and there are a number of other CCOs that have now been detected in other supernova remnants using Chandra observation. So neutron stars do all kinds of interesting things. They get formed in a supernova explosion. They can be highly magnetic. They can make pulsars. They all do all kinds of stuff. But one of the most interesting things they do, we found out about a year and a half ago, is that they can merge together. And so Chandra made important contributions to the revolutionary gravitational wave signal, or the study of the gravitational wave event that was also detected in electromagnetic waves. So here's the optical counterpart for the merging neutron stars. And these are there were X-ray observations taken of this. Initially, when the kilonova was first seen, there were not strong X-ray emission, but then it sort of ramped up over the following weeks and continued to get brighter. And ultimately, so this provided important constraints on the actual explosion mechanism in the kilonova. But in later times, there's actually been evidence now that the object is the sort of observed X-ray flux can give constraints on what is the object that's left over. So if the two neutron stars had merged together, in principle, they could have formed either a black hole or a neutron star, another more massive neutron star. But if they formed a neutron star, what you would have had was a rapidly spinning magnetar that would have produced a large amount of high energy emission. And you would expect that to be really bright in the X-rays. And so there's a nice paper by David Pooley looking at this, showing that the object is actually too faint in Chandra to be a magnetar. So in all likelihood, it's a black hole. So the picture is now that we have this merging neutron star that spirals in by these gravitational waves, and then ultimately the thing that's left over is a black hole. So we may have actually witnessed the birth of a black hole, and the sort of proof of that Chandra has made an important contribution to. Okay, so black holes then, now moving on swiftly to black holes. Black holes do all kinds of interesting things, and a vast amount of Chandra science is connected to black holes. I'll just give one example of, whatever are the thousands of papers on black holes with Chandra. And this is one that uses Chandra's, most of the stuff I showed before were observations with ACIS imaging capability, but these are observations with the high energy grating on Chandra. So this is GRO 1655, this luminous black hole binary. And this is a grating spectrum, so you can immediately see all this wonderful array of lines in the grating spectrum. You can learn an awful lot about the structure of this object based on the details of these particular lines. But the thing I want to focus on here is just the velocity of these lines. So if you take all these particular lines here, this was work by John Miller and collaborators, and you sort of plot them down and put them in the rest frame, you'll see that the observed wavelengths are shifted to the blue. And in fact, this is a several hundred kilometer per second outflow, which tells you that you have a very large outflow rate. And at least the conclusion in this paper, and I must admit I'm actually not as up on what the current thinking is on this, but the conclusion in this paper was that potentially that models of radiation driving of the winds could not produce that large outflow rate, and so there may be another mechanism such as magnetic processes that could drive such a wind. And so this is just one example of how these X-ray diagnostics tell you something potentially really important about the astrophysics of black holes. Okay, so I told you I was going to go fast. We're now done with the lives and deaths of stars part, and we're going to move on to larger scales, the growth and evolution of galaxies and black holes. And so we go from stellar mass black holes up to very much more massive black holes, and of course the one that we know the best is the one in our own Milky Way. If we look down towards Sagittarius A star in the center, this is a Chandra image of the very center of our galaxy. And as everyone in the room here knows, there's a 4 million solar mass black hole down in the center there. And so Chandra has been really important in studying what this black hole does, in particular because the emission down at the center of the galaxy is so complex. The black hole is accreting relatively weakly. It's not a really powerful quasar or anything. And so its X-ray emission is relatively faint, and in order to be able to tease that emission out from all the other stuff that's going on in the dense part of the galaxy, you really, really need high angular resolution. And so, I mean, this is just the central 3 parsecs, right, in here, showing all this diffuse gas, these black holes and neutron stars, all kinds of stuff going on. But if you zoom right in on the center, there have been many, many megaseconds now of or certainly multiple megaseconds of Chandra time spent observing this this black hole at the center. And one of the interesting things that they've learned is looking at the temporal variability. So this is a nice little movie that the Chandra Press Office showed about the put together of the source at the center here getting brighter as there are changes into the accretion flow onto the black hole. And so I showed in the at AAS, this isn't quite relevant because this is really a simulation of a more rapid accretion flow. But this is just showing a hydro simulation of accretion onto a supermassive black hole that actually has these nice light bending effects in here. But the point here is that this accretion process, and in particular acceleration of particles up to high energies, potentially, for example, by magnetic fields, are the things that produce the X-rays. And when we look at black holes sort of over the whole population, the X-ray luminosity is at least broadly connected to the accretion rate. And so in what will become important in just a minute, it's important to keep in mind the X-rays are basically tracking the growth of the black holes. And we can see this on small scales with, nearby with Sagittarius star, but also with very massive black holes at large distances. So one of the best examples of a black hole that we can see that's farther away, that we can really learn what's going on, is Centaurus A. So this is this nearby AGN. It's a merger of a spiral and an elliptical galaxy. You see this wonderful dust lane and then the sort of elliptical galaxy in the back here. This is what it already looks pretty amazing in the the optical images. But if you want to see where the action's going on, you can look at the hot gas or non-thermal emission. And so this is what the Chandra X-ray image looks like. Obviously, this is one of the most spectacular Chandra images. I actually had, when I was in grad school, before they made this multicolor version of this, I had this image as like the background on my phone. If you have one of those little flip phones, you know how you used to be able to put like a little tiny image on your flip phone? That was the blue version of this was the one I had on my flip phone. Anyway, what you can see here, of course, you can see the accretion onto the supermassive black hole in the center. I just love going back and forth here. You can see the relativistic jet, and you can see then on the other side, we don't see the jet so strongly in X-rays, but you can see the interaction of the jet with the interstellar medium or the intergalactic medium. And so this is this is a nice image, and then it shows a lot of the different processes of black holes and feedback that you can observe in the X-rays. So that's just one object, but of course, what we really want to know if we're studying black holes is how do they form and evolve over the history of the universe. And just one object doesn't necessarily tell you that. What you need to do is look at many of them and understand the whole statistical ensemble. And so that's where a lot of, at least my work in particular, and many other people's work with Chandra has focused. Another way of putting this is you have a question. You have one, if you look around at galaxies in the universe, most of them look something like this. They're just a regular quiescent galaxy, but every once in a while you have an AGN. And the question is, why are these different or the same? What are the actual processes that cause the growth of the black hole as an AGN? And so in order to study this, we have to do unbiased sort of statistical studies of the whole AGN population. And so this has been very powerful with Chandra, and in particular, Chandra has done a number of extragalactic surveys of blank fields of the sky that have been studied with many different wavebands. This one is near and dear to my heart. This is the X-Bootes field. This is the original 5 kilosecond exposure of this field. But now actually we have a much deeper program called the Chandra Deep Wide Field Survey that Alberto Massini, who's a postdoc at Dartmouth with me, is putting together. So keep an eye out for that soon. We'll have a even much better image of this particular 9 square degree region. But then, of course, Chandra has looked at many other fields, deeper ones. So a smaller area going deeper. This is the Cosmos Legacy Survey. And then if you go to a very small field, you get something like the Chandra Deep Field South, which covers a small area, but to extreme depth. It's currently got 7 megaseconds of data. And this is a nice representation of the most sensitive X-ray image ever taken. So why are X-rays useful for studying the growth of black holes in these galaxies that we see in these extragalactic fields? Well, in particular, X-rays are useful because they identify weak or obscured AGN that you wouldn't be able to find using other techniques. So we also traditionally have identified AGN in the ultraviolet and in the optical or through various characteristics in the infrared. But the problem is that all that kind of light is also produced by stars in galaxies or gas in galaxies, so that or dust, as it were, so that if an AGN is weak, or if it's obscured somewhat, then the light will be swamped by the light from the galaxy. And this is just a little representation of that. This is just a schematic, but a powerful quasar when observed in the optical and the X-rays. But if you dial down the power of the AGN, the visible light will be hidden behind the galaxy, but you could still potentially see the emission in the X-rays. So the X-rays allows us to probe much weaker accreting and more obscured emission from black holes than we would otherwise, which is critical for getting a picture of the whole AGN population. So this is the particular area that I work in. As Belinda said, my colleagues at Durham University and my group at Dartmouth do every 2 years, we do a conference on this particular topic, some element of this particular topic. So this is something, there's a huge amount of research, many thousands of hundreds, certainly probably thousands of papers that cover all this stuff. I don't have time to even come close to covering it, although I will say it looks like the next Durham-Dartmouth meeting will be next summer, 2020, and we're aiming to do that neither at Dartmouth or Durham, but since it's our 10-year anniversary, we'll do it in Iceland. Long story. So anyway, keep an eye out for that. That should be fun. And so I'm just going to really quickly summarize some of the things that, at least in my view, are the most important things we've learned from these surveys. One is that X-ray AGN are found in all types of galaxies. So they're not just star-forming galaxies, not just quiescent galaxies, not just spirals, not just ellipticals. Everywhere you see black hole accretion. However, on average, if you average up the emission from black holes and you compare that to the emission from star formation in those galaxies, or correspondingly just to the mass of those galaxies, basically big galaxies have black holes that are growing faster, and more rapidly star-forming galaxies have black holes that are growing faster. So these things are all sort of connected to each other. But instantaneously, in any single system, an AGN can have a very broad range in accretion rates that cover, several orders of magnitude. So they're not just light bulbs that switch on and off, but instead they are sort of covering a very wide dynamic range on relatively short time scales. And so the picture, once we began to understand this, a number of us began thinking about how should we actually understand the AGN population. And the traditional view had been, okay, what triggers an AGN? Some galaxies have them, they must have some discrete trigger. Now we realize instead that actually what probably happens is that all galaxies' black holes are growing on long time scales, but the triggers are things that are happening on small scales and that they flicker on and off. So you can think about any individual galaxy on the time scale of, say, 1 million years or 100,000 years, the black hole will actually be flickering in that time. And what you see when you look at the AGN population is a statistical distribution of all those accretion rates. In a way that's sort of comparable to a fluorescent light bulb being on all the time and flickering on and off. And while we came up with, right around the same time we came up with this picture, there were some great simulations that came out that actually started to resolve the accretion onto the black hole in an interesting way, and showed again that the Eddington ratios of black holes can vary by, in this case, 7 orders of magnitude over, say, 100 million years, which is the typical lifetime that you would expect a galaxy to change. So I think now this is really the picture that we have for how black holes grow. They're not just turning on due to some external trigger and then turning off again, but they are constantly flickering around, and in some ensemble sense, they're connected to the growth of the galaxy. And that's been kind of exciting for me to watch this sort of develop over the last 10 years or so. And the Chandra has really made a really important contribution to this in its extragalactic surveys. Okay, so we're done with the growth and evolution of galaxies and black holes. We'll move on now to the largest scales, large-scale structures in their cosmic history. So, as everybody here knows, the largest virialized structures in the universe are galaxy clusters. Here's the famous nearby Virgo Cluster right here, and you can see all the light from stars. This is an optical image showing M87, M86, and a whole bunch of other galaxies in there. But we know, as we said before, that most of the normal matter in this system is not in the form of stars, but it's in the form of gas. And in a galaxy cluster, the dark matter halo mass is so large that the virial temperature is very high. And so most of that gas will be heated up to even 10 million degrees. It'll radiate in the X-rays. So if you take an X-ray image of this same cluster with ROSAT, for example, this is the best I could do trying to stitch these two together. But what you can see is there's this very diffuse halo of X-ray emission, and then the center of the dark matter halo here, centered on M87, you get more and more denser and hotter gas down towards the center there. And then, of course, some of the other galaxies have their own halos inside there. Now, when you, as many of you are aware, so we have this picture that there's all this gas that's heated to high temperatures inside these clusters, but there was long a problem in understanding this, and that is that if you go into the very center of the cluster and you compute the cooling time of the gas just based on its luminosity and its temperature, the cooling time is really short. And so you would much shorter than the age of the universe, or at least comparable to the age of the universe. So you would expect all this gas here to be cooling out of this hot phase and then eventually down into a cooler phase and raining onto the central galaxy and forming tons of stars. But we just don't see that. Central galaxies in clusters have some star formation, but they're really very small, much less than you'd expect if all this gas were cooling out. And this is the famous cooling flow problem that was a real issue in the formation of structure for a long time. So Chandra really helped revolutionize our understanding of this. If you take M87, you zoom in high resolution with Chandra, here's again the optical image. You can immediately see the black hole is doing something interesting here. Here's the relativistic jet in the visible. But if you look in the X-rays, you see this amazing image. And Bill has better versions of this that like show all the different things, but this gives you at least some idea of what you see. Look, you just see this amazing structure. You see these arms. This material is going all over the place. There's a shock on larger scales that you can see. And I'll just focus right now on these bubbles in the gas that you see that are, we now know, have been inflated by the jets from the supermassive black hole. And so this is a nice animation that the Chandra team put together, the EPO team, just showing, you know, what you might see here. Here's your relativistic jets from your black hole, and oh look, they're blowing big bubbles in the intercluster medium. But this is actually what we really do think is happening here. This isn't the only place that this happens. If you go to the center of the Perseus Cluster, another nearby cluster, again you see these big holes. This one doesn't look that great. There are better versions of this too. But you see these big holes again. And one of the cool things about X-ray observations is that we can understand the hydrodynamics of the X-ray gas pretty well. So you can do actual energetics of this just using basic thermodynamics. So ultimately, let's take this this cavity here. You can look at the X-ray gas and work out what the temperature and the density is. You know what the gas pressure is. And you know what the volume is here, so you can show the work, the amount of energy that it actually took to inflate that bubble. That, of course, we think ultimately was produced by the jet from the supermassive black hole. And you can do this not only on this system, you can do it even on much bigger ones. This is the famous cluster MSO735, which has a humongous cavity here that's 200 kiloparsecs across. And this is now showing, the pink here shows the radio jet actually actively filling this cavity. And so over this wide dynamic range and scale, you can begin to do these kind of energetics and ask how much energy was pumped into the system by the black hole. And so then you can make a figure, which is the cavity power. This is with some assumption about the intermittency of the cavities being inflated. You can work on how much energy it took to, the rate at which energy is being pumped in, and compare that to the cooling luminosity. And if these are matched to each other, then the black holes pumping these cavities is offsetting the cooling that you would expect, and this would solve the cooling flow problem. And indeed, when you do it, you find a remarkable correspondence for this over many orders of magnitude. Now, I saw Paul here somewhere, Paul Nelson. He's going to tell you all the horrible details of this. I show the simplest version of this plot without any, equations of state or anything like that on there. But anyway, the basic conclusion that black holes can regulate the baryons in the universe on large scales is something that was critically a critical contribution of Chandra. Okay, so getting near the end here, Chandra also didn't necessarily just understand the formation of structure. It actually gave us some hints about the fundamental nature of the universe. And one of the most important observations was the bullet cluster, the famous bullet cluster, where we were able to look at the distribution of matter from weak gravitational lensing. So these are observations of the shape distributions of background galaxies in this system. And so the blue here now is showing the total mass distribution integrated along the line of sight as inferred from lensing measurements. And so what this can be used to do is actually test the nature of the material that actually produces gravity. So if you imagine, people have suggested other alternatives to dark matter, which we know is the dominant contribution of the matter, component of the matter in the universe, or at least we think so. If that were not true, if normal matter was the dominant contributor, then the normal matter should just be sitting right on top of these structures here, because they're the things that are producing the gravity. And the nice thing is, in a galaxy cluster like the bullet cluster, most of the normal matter is at high temperatures. You can see it directly from the X-ray gas. And so there was a famous Chandra observation led by Maxim Markovitch of this, and this shows now where the normal matter is. And you can see right away it's not on top of the dark matter. And so this offset is direct observational evidence, indeed, that most of the mass in this system is dark matter. What actually is going on, you see this this particular feature showing the material getting pulled off this smaller cluster. Well, what you have is a small cluster traveling through a large cluster, and the interaction between those two strips the baryons away from the matter potential in the smaller cluster, and you end up separating out the normal matter from the dark matter, which of course does not experience friction or hydrodynamic forces, and so the dark matter just continues to carry on through, but the normal matter gets separated out, and this is a simulation showing that. So this teaches us not just about the fact that there's dark matter there, but also something about the way that normal matter interacts with itself during, for example, the collision of galaxy clusters. Okay, I don't have time to go through any of the details, but I would be remiss without not to mention the fact that Chandra observations have been critical also for our understanding of cosmology. Because they're great for measuring the masses and the properties of galaxy clusters, they can allow us to work out how many massive objects there are in the universe, and that itself is sensitively connected to what the fundamental parameters of the universe are, like the mass density or the strength of dark energy, etc. And so Alexei's done a lot of work on this, and there's many other people in the room, I'm sure, who have worked on this, but Chandra has been a key component of our understanding of cosmology from the galaxy cluster perspective. And that's just one of many examples of the kind of work that Chandra has done in that regard. Right. So there we go. We've gone through 20 years of Chandra science. I hope I've given you at least a little bit of a flavor of what the remarkable kinds of things Chandra has been able to do. Just a couple things to wrap up. One is that Chandra is good to go. It's 20 years old, but at the moment there are no showstoppers for at least 10 more years of operations. So that's very exciting for us, especially as it may bridge us into the next generation or close to the next generation of X-ray observatories. But an important question is what comes after Chandra. And we need to begin thinking about that now, of course. And there are many different arguments for building a new X-ray telescope that would come after Chandra. But one of them, to me, is just the question of how do you go deeper. So this is the Chandra Deep Field South, that very, very deep 7 megasecond observation. And these Chandra Deep Fields are near and dear to my heart because they were actually the first serious Chandra data that I worked on. I was a grad student here. I started working with Christine and Bill and Steve Murray and Maxim Markovitch. And Christine said to me, "Oh, Maxim and I were talking about this project. We have this great project. We want to get your feet wet with Chandra data. So do this thing. We want you to measure the unresolved X-ray background in the Chandra Deep Field, north and south. That should only take you about a month." So, as I mentioned, any of the grad students in the room who are the senior grad students will know that when your advisor tells you that, you should be highly skeptical. It turned out more like a year of working deep through the night with Maxim Markovitch, if anybody knows him, especially before he became a dad. That was his working mode, so I spent a lot of nights here. But we ended up doing that. We actually cut out all the X-ray sources in the Chandra Deep Fields and measured the strength of the signal that was left over, this extremely faint X-ray signal that really required Chandra's resolution to do this. And so this sort of goes back in my history, the idea of getting very deep as you can go is exciting. Now we know that hidden in this unresolved signal are really interesting objects, very high redshift galaxies, and some of them may even be signatures of the first black holes. And so how do we see this extreme faint X-ray signal that gives us clues about the early origin of the universe? So to do this, we need three things. We need high sensitivity, or two things, and exquisite angular resolution. And those two requirements are really some of the main drivers for the development of LINX. So many of you are familiar with LINX. It's one of the 4 missions being presented for the 2020 Decadal Survey. And the idea is that it's a observatory with resolution comparable to that of Chandra, perhaps even better, certainly better over a wide solid angle, but with a significantly larger, orders of magnitude better sensitivity. And so observations with LINX, this is just a simulated 1 megasecond observation, would allow us to identify the earliest growing black holes at redshift dV up to 10 or larger. And there are many people here that are working on LINX. You can ask them or me whenever you like, but it's a really, it's one of the main science drivers for LINX and is really, really exciting and powerful. And so LINX as a observatory, this is one of the stock LINX slides, would cover not just its dawn of black hole science, but also, as we've seen, understanding the drivers of galaxy evolution and the energetic side of stellar evolution. It would really touch on all of the various science topics that has been revolutionized with Chandra. Okay, so the nice thing is that the future for X-ray astronomy, there are many possible avenues forward. These are currently operating X-ray telescopes. LINX is one potential future mission. Another one, which many of you here are involved in, is Athena, which is the large flagship European mission that has a similar large effective area like LINX, a somewhat different suite of instruments, and doesn't quite have the very sharp angular resolution that LINX does. These are really quite complementary, sort of like XMM and Chandra, really. Then we have a whole suite of missions that are either definitely going to happen or are well along in development, and a number of other future concepts. And so the future of X-ray astronomy is really bright. And so that's nice looking forward. I'll just leave this slide up to say thank you to everybody here who helped, in particular, who helped make all this stuff possible, and also to, in particular, to my advisors and mentors, Christine Jones, Bill Foreman, and the late Steve Murray, who we all loved. And I didn't take this out. Thank you to the AAS. One last thing I will do, I have Christine in the corner over here. One last thing I will do is the AAS election closes tomorrow, and I said this and I'll say it again. Please, I'm on the nominating committee, so I have a skin in this game. Please vote in the AAS election. And with that, I'll say thank you very much.
Anyone have any questions?
Did the 1963 proposal actually use grazing optics?
That's actually a good question.
Yes.
Yeah.
It had rocket flights, it had what became the Hickox, and it had a 10-meter focal length, 1.2 meter double grazing instruments, our second scale optic. And it was ready within 1 year of the discovery of Skill X1, and we went straight back. So, mirrors didn't exist, the detectors didn't exist, and most of the rest didn't exist. But our envision doing it in a 5-year time frame. Took a little while.
Yeah, can you give a brief overview of what LINX would do for, say, the life and death of stars?
So it's hard to give a brief overview.
I mean, compared to Chandra.
So one of the big things that LINX will do is further study that really blow open this field about identifying young protostars and forming stars in star-forming regions. So right now, Chandra can really only go out to, the numbers are now escaping. Do you remember what you said? It's sort of something like that, yeah. So, several hundred parsecs, a few hundred parsecs is the farthest out we can go with Chandra to be able to do the kind of science that I showed here. And so there are star-forming regions that Chandra has been able to do this with, but given its sensitivity, there's only a handful that have really gotten good statistics on young stars. LINX would be able to go, because it's about 100 times more sensitive, would be able to go out 10 times farther. And all of a sudden you've opened up a much larger volume, both in terms of not just having more star-forming regions, but also having different star-forming regions. The more distant ones, some of them are forming inside the giant molecular clouds. They could have potentially many different properties, and so you've gone from being able to only kind of see the star formation that's happening in our environment to being able to probe a much wider range of it in our galaxy. So that's one of the main drivers. There's also a lot of really great supernova science that sort of does similar things, both going deeper on the observations, on the objects that we already know about, and being able to probe supernova remnants much farther away. Those are just two examples, but there are many others. And I would encourage you to go look at the LINC's website, or we have a lot of promotional materials, talk to Alexa. There's a lot of exciting science there.
Anyone else? Well,
Okay.
thanks for
Thank you
having
very
us.
much.